Hello everyone. My name is Aditya. I am a PhD student in National Center for Biological Science, TIFR here in Bangalore. Uh, I study biology in my daytime, and I am a big uh, fan of astronomy in the uh, rest of the time. So I joined BAS 2-3 years ago, and I have been learning ever since. And I thank everyone to give me the opportunity to present what I would like to talk about today. So something that is very close to my heart, and something that has shaped my science is the power of do-it-yourself science, the power of small experiments, the power of very very less complicated setups that can tell us a lot about very fundamental things. So I will share with you guys three or four such stories, and we'll also have one calculation ourselves at the end to have some fun. So this, I hope it's going to be interactive talks. So if you have any questions, please put them in chat box, or you can actually directly ask when the organizers allow. So okay, so let's begin. So today I thought I'll talk about two of the most fundamental um, aspects or facets of astronomy, amateur, professional, otherwise also. So those two are gravity and light, and it's needless to say how important their interactions as well as they are in our understanding of the universe. So I'll share with you few things about gravity and light, how very fundamental uh, aspects of these two forces were revealed at different stages, and mostly in classical paradigms, in classical context. And we will also take one example which is very recent, and that's very interesting. And okay, so let's begin. So what do I mean by simple experiments? First of all, simple experiments are those experiments which do not require much complicated interdependent set of systems. Very simple, just like, for example, a stick, as primitive, as simple, as easy as that. So an example which drives this point home is the example of Erastothenes. So he was a very multi-talented polyglot guy. He was in ancient Greece around 300 BC. He worked on many things, including astronomy and mathematics and philosophy. So he was one of the first person to accurately measure the tilt of Earth. But what I'm going to show you is another simple experiment that he did. So he used to uh, live in what's the current Egypt, and that time Alexandria. And he used to do almanac keeping and measurements. So and you guys must have heard of zero shadow or no shadow day. These days occur on particular day twice a year at every location within the two tropics on the Earth. The special thing about that is the sun is directly overhead at that location, so so any object that is on the ground wouldn't cast a shadow anywhere else but right underneath it. So Erastothenes got really interested in that, and he thought he'll use that with some assumptions to measure how big the Earth is. So he lived in Alexandria, and there was another city downstream Nile, which was called Seine, which was in those times measurement 5,000 stadia. He got measurements in the sense that he assumed. So, by the way, Seine is just above the Tropic of Cancer. So he assumed that when the sun ray fall at Seine, here is Seine, and assuming that on that day Alexandria was too north to have zero shadow day, but Seine was right there. So on one of the days, he took multiple measurements with his team, I'd say, and then they measured how much angle does a minaret or, in technical sense, a gnomon subtend on the ground. If we assume that the sun is a distant light source. So he then measured the angle that this would create, and a simple mathematics can tell us that this angle that you see here between the line joining the two places and the center of Earth will be equal to this angle. Now, if you have this distance here, which is okay. So I was explaining how Erastothenes, who lived in Alexandria, did the measurements then. So at Seine, which is further south, which at that time, from that time's almanacs and surveys, found out to be 5,000 stadia away. And so what they did was they just used the angular separation, went ahead and measured the angle that a gnomon would subtend, the shadow of a gnomon would subtend. There would be no shadow in Seine, and they knew that Alexandria and Seine are separated by 5,000 stadia. Now, a simple geometrical exercise will tell us that if you look at this angle which the shadow makes, is same as this angle which the gnomon as well as the any object at Seine would make at the center of the Earth. And similarly, so what's fascinating about this is that you can do this at your home at any time when there is a zero shadow day to compare with, or even if you have angles that you can compare. So I'll show you. So you can also do these experiments really easily. So this is one of the examples where we did a similar experiment. What you see here on the left is an example of any regular day at Bangalore, but on that day where the measurement was taken, there was zero shadow day in Bhopal. So if you can see, even in the direct sunlight, the sunlight is directly falling straight through the pipe and therefore casting no shadow around. So if you now go to Google Earth or Maps, you'd see a Google map picture of Bhopal, which is at 23 degrees north, and Bengaluru, which is 12.97 degrees north. If you look at the distance between the two, it turns out to be 1,129 kilometers. And if you just take a difference of these two coordinates, and you will get the angular separation of the two locations. So on that day when there was no shadow in Bhopal, but there was a shadow in Bengaluru, there was the angular separation of 10 degrees, because that's the separation between Bengaluru and Bhopal. Now, if you do a simple maths, like if 10 degrees translates to 1,129 kilometers on the surface of the globe, how much will the entire 360 degree make? And that would be the circumference. And if you do multiplication of 36 with the distance, you get 40,651, which is circumference. And of the Earth. Now, there is some assumption here that Bengaluru and Bhopal need to be right. So if you use Google Earth to measure it and calculate the circumference of Earth, it turns out pretty close to the. There are some assumptions that Erastothenes also took in his time. For example, that the Cyan and Alexandria fall on the same line. Actually, they don't, but they're pretty close. And they also had to assume the take such simple measurements as simple as measuring the angle of shadows at two different places, uh, and knowing the distance between these two places, you can know where how big the globe, the ball on which you're standing is. That's, I think that's very profound for me. That's so just to show the calculation again in case I missed it. The angular separation between Bhopal and Bengaluru is almost 10 degrees. 10 degrees translates to 1,129 kilometers. And that means that 360-degree would be around 40,651 kilometers. And the average circumference is not very far off. So simple experiments like these you can do any day, you can do on your roof or wherever, and they can tell you a lot. Is something that's very fascinating. So let's switch gears and let's look at something big. So this is about the quest of weighing the Earth. Well, the we knew the radius from quite some time, the circumference and radius and everything. For the theory that Newton gave, to prove it, we needed a little bit more. We needed to know the mass of the Earth, or we needed to know the density, because we had the radius, so we had the volume. Density would have also worked. So Newton actually, in his original research, only talked about ratios. He suggested that the ratio of masses, or sorry, densities of Sun, Earth, Moon, and so on, would be in this and this proportion. And at that time, ratios were all that were important, because once you have one value, you can quickly calculate the rest. And that one value was that was needed was density of Earth, or the mass of Earth, the same thing. So there were many suggestions. There were many attempts also. It was suggested that if you if you if you hang a pendulum, and if you hang a pendulum near a really massive object, that pendulum should not only get attracted by the Earth, so it will be hanging down, but the massive object will also pull slightly the pendulum towards it. And if you can tell what angle the pendulum rests at, you can tell how much equilibrium, or how much density, what's the ratio of densities of that massive object versus the Earth. So people suggested what's the massive most object on the Earth one can find? Mountains. So there were suggestions that maybe we can hang a pendulum near a mountain and tell how dense the Earth is. So Newton, who originally proposed the need to measure the density, did not like the idea. He said that, or he did not like. He was pessimistic about it. He said this won't be the force of gravity is not strong enough to show any noticeable difference in the deflection in the angle of the pendulum. But people carried on nevertheless, and that was fruitful, because at some point Royal Society could fund an expedition where they found a mountain which in northern UK was found to be nearly symmetrical and alone, as in there was no other massive mountain or hill or any object nearby, and it was just standing tall and alone without any other gravitational influence. So the expedition lasted 2-3 years. What basically they did was shown here in the schematic, the cartoon on the right. They just hung a pendulum on one side of the mountain and let the pendulum come to a rest. If there were no mountain, the pendulum would rest absolutely vertical, as in if you trace the thread of the pendulum, it would point directly to the center of Earth. But because there was some sizable mass in the mountain also attracted the pendulum, and that caused the angle of the pendulum to deflect from 0 degree or perpendicular to some angle. And to improve the accuracy in that, they took measurement on either side of the mountain. So if you imagine a mirror image of the cartoon here, you'd see that the pendulum, if taken on this side, would deflect again towards the mountain. So they can do double measurement with the single mountain, and that's what they did. And the results were pretty good, although there was uh, an error of around 10 to 15% in the measurement of the density. Basically, what they did was they had to measure the volume of the mountain. And once they had the volume of the mountain, they also could calculate the mass of the mountain or the density of mountain just by measuring a specific amount of chunk of the mountain. Now, this brought us close to the now accepted density of Earth, but with some error. But that was not worthless, because it, although could not prove or bring us closer to the actual value, but it certainly proved one thing, and that one thing was a leading theory at that time, a hypothesis at that time, which actually Edmund Halley also used to believe in, which is that the Earth can be a hollow globe. So the density values that came out of this experiment showed that the density is so high that the crust, the measured density of the top surface, the crust of the globe, cannot account for that. So there must be something heavier under the crust or inside the globe. Therefore, the globe cannot be hollow. So that was something really fundamental that came out of this experiment. Although not very accurate or precise, this told us something. So that was very interesting. But what really drove home the experiment for a long time, it was very accurate measurement, was Henry Cavendish's experiment. So Henry Cavendish was a chemist and physicist working at Royal Society. There was a physicist before him called John Michell, who designed a torsion balance. A torsion balance is something like a pendulum, but you can imagine it as a double pendulum, in the sense that if you look at the diagram here of Henry Cavendish's balance, you see these two red dots appear here. These two red dots are tiny pendula, which are suspended from a wire from the ceiling, and that wire connects the two pendula with a wooden rod. So this was the torsion balance design of John Michell, and Henry Cavendish inherited it. The experiment was also very simple, which is why we are discussing it here. So Henry Cavendish improved the design with a very good significance. What he did was he isolated the entire system uh, into a thick wooden box, so that he doesn't his mass or his movements don't influence the pendulum, because pendulum would get attracted to any mass around, and if there is any moving mass around, the pendulum would move and the angle would change. It's very similar to the mountain experiment, but kept uh, as undisturbed as possible. So now so then he caged the whole system into wooden box. Um, but now we cannot bring mountain inside, so we need something else, something more massive than these red small pendula. And that massive thing was two giant lead spheres that Henry Cavendish put. So these spheres were around 160 kg each, that he brought into the system. And he designed it in such a way that they can be lowered or removed from the influence. So you can put them and uh, then record the experiment, or you can remove them. So this is just a schematic diagram of the setup. How it would look in real life, or a small version of it, is one thing important is that since Cavendish did not want his own body mass to influence the whole setup, he designed a small hole in the cage, and he used a telescope, and he would sit outside and record the movement of pendulum from far away. So that also increased the precision. So it looks like the system has become complicated now, but what actually essentially has happened is that he removed a lot of sources of error. So that was something that improved the precision of the system a lot. Now, this is a modern day version of the same pendulum, or the same torsion balance. What you see here, I hope you can see my arrow, uh, are the two lead balls here. These are the two red spheres. They are hanging. Hello?
Yes, sir,
Uh,
we can see. We can see your
okay,
arrow and your X.
cool. So they are hanging from a wire here in the middle, and supported by a rod. Now, this could be attached to just forgive the bad image quality. This is taken from a video. um, these are the two giant spheres. These are not so giant in this tabletop working model of the torsion balance, but in actual experiment that Cavendish did, they were huge. They were 160 kg each. So what that would do is cause this pendulum to move around. So I'll show one experiment that is done recently in a laboratory. This is sped up. What you what you see here is this is the pendulum, and we are seeing from top. There are these masses on either side, and this time is for showing how fast this equilibrium setting is. Now, this pendulum oscillates, of course, at certain point, but as soon as you put the the heavy metal blocks, you see that the position has suddenly changed, and now the bar and the masses, they look clearly getting attracted by these blocks. So this is how this works in action. Now, to measure this, how do we measure it? How do we measure how much the angle has changed? Because now we cannot physically access it. So what Cavendish did was he fixed or glued a mirror on this wire. What Cavendish did to actually measure how much the deflection of pendulum is, he fixed a mirror on this green wire here, and and then directed a beam of light on the mirror, and the reflection of the beam of light from the mirror could be read on a scale with vernier gradation on it. So then he would read the scale from far away using a telescope through a hole. So that was the design, and it worked. It worked so well that the precision in his measurement was unmatched for next 150 years. He could show that the at the equilibrium position, the tension in the wire because of turning is caused by the gravitational attraction of these heavy lead spheres. And if you put them together, uh, you can get the time period of the pendulum, just like a mountain. Instead of mountain, now you have a heavy lead ball, actually two. So this was the end formula. And assuming that the density of lead is 10.5 times that of water, he could easily calculate that the density of Earth must be 5.48 times water to have a certain degree of deflection in the torsion balance in the pendulum. So again, another example of a really simple setup made precise by putting more efforts into it, but giving very profound results. Profound in the sense that once you have density of Earth, you know the mass of the Earth because you have the volume of the Earth already. And if you have mass of the Earth, then as suggested by Newton, you can get mass of the Sun, mass of the Jupiter, mass of the Moon, just by studying their orbital dynamics, just by studying how Moon goes around Earth, or Jupiter's moons go around Jupiter, or Earth goes around Sun. So uh, straight. So from these experiments, you have far-reaching results. So that is something really interesting. Next, I would like to show you.
I have one question.
Yeah, go ahead.
Do you know how he got the torsional constant of the wire? Because
Yes.
there has to be some other way to calibrate how much
Yes,
the wire
absolutely.
will twist, right?
Yeah, absolutely. So what he did, I'll go back to the formula. If you see the formula here, on the right side, there is the time period T and arc by L, which is the angle of deflection. So the time period of the T depends on the force. And what he did was he took the ratios, because at that time it wasn't important to get the absolute values, but it was enough to get ratios. So what you would do, or what he did, was he removed the huge lead spheres and measured the time period. And
okay, got it.
that turned out to be something. That turned out to be, I think, under 4 seconds. And then he put the huge lead spheres, and then again measured the time period. And this time there were two forces acting against, and the time period was something else. So then he just took the ratio. So
perfect. Thank you.
Yeah, that's one way. Or you can measure it outside the setup.
Cool.
For a given material of wire. Yeah. Okay. Any other questions?
And Aditya, there was one question on the chat window. So I think it pertains to the previous topic. So Earth is also tilted on its axis. So does this make difference in the angle of shift from 0 degrees? Probably for the Newton's pendulum experiment.
No, it doesn't. So it doesn't matter if Earth is tilted, or in fact, it doesn't matter in the context of that experiment where the Earth is situated. The Earth can be free floating in space, not rotating, not in the orbit of Sun, and all of those experiments would work. The only slight requirement was that they used stars to measure the angle. So if the Earth would be free floating, then you would measure the angle in some other way. But otherwise, the tilt of Earth is not important here, because the angle from the vertical, which means the line going directly to the center of the Earth, is the reference point, and then you measure the deflection from that. Does that answer your question?
Yeah, I think it should.
Okay. Okay. So let's move ahead. Yeah. So after, actually not after, this is a slightly anachronistic. There was another really long-standing problem or an idea that needed to be tested. So Aristotle suggested that heavy things should fall faster towards the Earth. That is intuitive because it's hard to see acceleration happening, and it's hard to see heavy and light objects fall at the same rate. And since there is air buoyancy and friction, all these things come in. So Aristotle gave this idea that if you drop two things, one heavy, one light, they should fall at different rates, and the heavy thing should fall first. It should touch the ground first. So, but I think many of us know Galileo had a different opinion on that. And he had conducted some experiments like dropping things from the Tower of Pisa, although it's considered anecdotal. So there were experiments that he was trying, and it wasn't so easy to do that. So here comes the interesting and the simplifying part. Now, Galileo wanted to solve a problem. He wanted to slow down the things so that he can measure if they're falling faster or slower. Now, how would you do that? And Galileo came up with a really simple but ingenious idea, which was he realized that if you throw things from a particular height, they fall together. I mean, that was the thing that he wanted to test, but the end result would be the same. So what he did was he created an inclined plane with some angle. What that did was that reduced the component of gravity that would act on any object that would roll on the inclined plane. So that means you have reduced the force acting on the object, and therefore, if the force is less, then the acceleration should be lesser too. Ideally, if you want to prolong this, you want the angle to be as shallow as possible. So you can imagine that if the inclined plane is so obtuse that it is almost vertical, then the thing would just fall. But if you keep the angle shallow, it will roll for a long distance and for a long time. Now, there was another problem. That problem was that there weren't precise clocks at that time. Now, what do we do? If you cannot measure time, then you cannot measure speed or acceleration correctly. So here comes another ingenious idea, that he asked his students or I don't know, colleagues or maybe himself to sit with a barrel of water. I'm showing here wine, but it actually was water probably. So what he did was he rolled a spherical ball of different masses from different distances on this inclined plane, and then as soon as they would reach the end of the inclined plane, as soon as he releases the ball from the inclined plane, he would start the tap, and the tap would fill a vessel with water. Now, as soon as the mass rolls down the inclined plane and reaches the end of the plane, he would immediately stop the tap. So that means that he is collecting water, which is proportional to how much time a an object is spending rolling on the inclined plane. So without any need of clock, he was able to measure how much time an object is spending on the inclined plane, or how much time the object is spending falling down the inclined plane. And when he did that from different heights with differently heavy objects, he found that the mass of the object doesn't matter. It's always all the objects fall in such a way that they fill the cups of water or the vessels of water in the same identical ratio. And that ratio turned out to be, if you can see the pattern here already, turned out to be a series of squares. So that gave a glimpse into how the distance traveled by this object, by the ball, will be. The distance should be proportional to the square of the time. How much time it spends, it travels square of that time distance in that time. And that was another hello.
Hello, yes, it might be the acceleration of that body.
Correct, yes. Yeah, since the acceleration of all the bodies of different masses was constant, the time taken would be the distance traveled would be proportional to the square of the time taken. The time here being measured as how much water is being collected in the vessel. Okay, so there's another very insightful thing that comes out of this simple setup and simple experiment here is the equivalence principle. Maybe we can discuss the equivalence principle in the end if we have time. Just remind me again when we finish the talk.
Sir, if you just state it, what does the principle says? Just a statement.
Surely, yeah. So it's not very. It's not necessary that how much inertia an object has is also going to be the same quantity on which gravitation acts. So if you remember Newton's gravitation formula, force is proportional to mass and inversely proportional to the square of radius. So let's just look at the mass right now. So if the mass increases of moon in Earth-Moon system, then the force on the moon that is exerted by Earth also increases. Yes. So that is the gravitational mass, which means in the gravitational force, how much mass is acting from the moon side. And but when the force acts, a body accelerates. So, and the body accelerates in proportion to how inertial that body is, how massive that body is. And it is not necessary actually mathematically that this inertial mass is the same as gravitational mass, and that is the equivalence. Is it equivalent or not? And most people agreed that it should be similar. The ratio of these two masses should be close to 1, if not 1. So that is the equivalence principle. And this thing here, really simple, inclined plane, rolling the ball from just the slope, proved or helped proving that yes, indeed, it is the same. So if there are questions on this, we can take it in the end on equivalence principle. Okay, so I would like to now switch gear to from gravity to light. Which is another fascinating thing that connects astronomy. Okay, so light is has been a very hot topic of discussion and debate and theories and hypotheses, and there have been it wouldn't be wrong to say academic fights over the nature of light, the speed of light, the properties of light, and so on. So it was believed that the light travels at infinite speed, which was the was a long-standing puzzle. If the light travels at infinite speed, or if it travels at a finite speed, what is the speed? And there were attempts to measure that. One of those attempts came from finding an error. That error was found by a scientist named Ole Rømer. So he was working on the longitude problem. Longitude problem, I'll just briefly tell, was a problem faced by the voyagers when they are out in the sea. They cannot know which longitudinal meridian they are in. So there were many solutions attempted to find what to design methods to find out what the longitude of the ship is. Galileo suggested that we measure. So to measure the longitude, you need to keep a track of time. Now the problem was that there weren't precise clocks available that time, or you wanted a clock that would work anywhere. It need not be synced from your base station or base port where you started with. So Galileo suggested that we can use the motion of the moons of Jupiter. That was very well recorded by himself. We can use the orbital motion of the moons of Jupiter as a clock that is up there and everyone can see it through the telescopes. So that kind of worked for some time. And why it only worked for some time was because Ole Rømer found out that there is a discrepancy in the observation or in the visibility of the moons. So Jupiter moons go behind Jupiter and come back out, and they can be precisely timed when they should come out and go back behind Jupiter. But that precision table that was, by the way, created by Cassini, started giving errors. And Rømer realized that error is in positive when the Earth is in summer and or on one side, let's say, of sun, and that error is in negative when the Earth goes around after 6 months on the other side of the sun. And this error was not explainable by any other means, only if the moons of the Jupiter have a variable orbital speed, or if there is some kind of delay in the light coming from these moons to Earth. Only these two things could explain. Now, variable orbital speed cannot exist in stable planetary systems. So Ole Rømer then immediately hypothesized that no, it should be the problem. It should be because of finite speed of light, that it's actually taking positive. It's delaying when it is coming, when the Earth is going away from Jupiter, and when Earth is going towards Jupiter, we are seeing the moons before our predicted time. So Rømer gave a hint that yes, the light has some finite speed. It's not infinite, but it's really fast, because the error was even lesser. Now there was a guess. Cassini and Huygens were at Royal Society. So Ole Rømer submitted his data of observation of Jupiter moons to Royal Society, and Huygens crunched the number and found out that if there is the error was coming out in Rømer's observation to be 22 minutes plus minus 22 minutes, and if that is coming because of the distance of Earth from Jupiter in its orbit, then the diameter of orbit should be accounting for that 22 minute. So if that is the case, then if you divide the diameter of the Earth's orbit by the the discrepancy, that is 22 minutes delay, you should get how fast the light is crossing that diameter. And that came out pretty close to the speed of light that we know now. Okay, so but that wasn't precise enough. It was in the same order of magnitude, but around 25% error. Now comes another experimenter. His name was Fizeau. So what he did was he was working on a geared mechanism. Now this is another simple yet very ingenious experiment. He had this geared wheel here that you see as toothed wheel. What he did was he had a source of light, and using a mirror, he would shine light through the teeth of the gear, and then let the light travel a long distance before it bounces off a mirror. Now the light has to travel another long distance back, and through the teeth again, it would strike the mirror, and this mirror, being a partially reflecting mirror, would allow this light to pass through and to be seen. You can put a screen here, or you can see it yourself. So now he said that since light is traveling really fast, let me increase the distance and let the light travel more so that I can buy some time. Another way of buying time was that he could rotate this wheel. By rotating, what he could do is he could interrupt the light, because the light would then strike the teeth of the rotating wheel, and then go to the mirror, come back, and again strike the tooth of the geared wheel in a manner which looks like this. I hope everyone can see this. Am I audible? Hello?
Yes, Aditya, you are audible.
Yeah, just was making sure. So, okay, so here is how. So you see this cyan or the blue colored, that's the light photon coming from mirror. It has passed through one of the gaps between the teeth, has gone to the mirror and has come back. And now if the speed of this geared wheel is adjusted in such a way that the bouncing photon, not photon, but the light beam strikes the gap between the tooth, then it will be obstructed. Now what you do is you say, okay, I have 720 teeth in my gear, and I'm rotating at 12 RPM. When I do that, then the light doesn't pass through. Every time the beam of light passes through the gap of the tooth, the distance is so that the returning light it hits the tooth and doesn't go back. So I don't observe any light on the other side. Therefore, the light beam is striking the two consecutive teeth in the gear system. Okay, so that leads us into this tiny calculation. You say, okay, number of teeth in the gear is 720. I'm rotating at 12 RPM, and the light, I'm making it travel 8 plus 8, going 8, coming back 16 kilometers. So when the light travels 16 kilometer, the gear rotates just one tooth. And how much time it takes when it's rotating at 12 RPM to rotate one tooth is this much, 17,280th of a second. And now it's very simple. You just distance upon time is the speed. So you say, okay, the light travels 16 kilometers and the time taken was this much, and lo and behold, you get a value which is 2,76,480 kilometer per second. And if you remember the speed of light that we now have fixed as a constant, it's 299,792. So that comes really close, much closer than the earlier experiments. So here I have presented another simple design, but really far-reaching experimental results. something as fast and um as fast as light could also be slowed down enough for us to measure. So that's something that this design allowed us to do. Okay, so now we are in the last part of the talk, and this is a bit more to do, like hands-on. So I'll show you what I'm doing. Basically, what I'm trying to show is that in the current times, this talk is still relevant. Whatever I presented, we have data that are released by space agencies, European, NASA, ISRO, and so on, that even us amateur astronomers, actually more us, because that's what we can do from our home. We can do. We can look at these data. We can look at patterns. We can crunch these data. We can we can calculate. We can measure. We don't have to obtain the data, but we can surely measure, and that is what I'm going to show you from this one. So this is a measurement of the mass of the supermassive black hole that sits in the center of our galaxy Milky Way. That black hole is called Sagittarius A, and I have taken data from European Space Agency's data servers. So before going into what the data is, let's look at what the observation, what the experiment is. So over a period of around 15-16 years, maybe more, using the power of Hubble telescope and so on, scientists took snapshots of stars that are in orbit around a really massive body. How do we know it's massive? Because the orbits of the star look really elliptical, and the speed at which these stars are orbiting is really fast. Okay, so this is a video made from such snapshots. Since these are stars and they are traveling distances that are light days or light years in magnitude, these snapshots are taken at months or years apart, and they are put together into this video. So what you see here, and I just remembered, Prajwal ma'am also showed this in her talk a while ago, 3-4 months ago, and I'm sure it's available on YouTube. So what you see here is so many stars here, these blob of light. They are orbiting around something. If you follow almost in the center where my pointer is, you'd see that there are these whipping actions that these stars are doing. If you look at this one, and now if you consolidate all of these snapshots into trajectories, here are 3 of them, and similarly there are many stars that are plotted here, so with the scale bar. So now let's come to what we can do. So European Space Agency has released the positions of these stars, and this is a sample from that table. What you see here in the first column is the date of the sampling, the date of snapshot, and in the second column you see the X position of that star in the XY coordinate system, and dx is the error. We can ignore this for our purpose today. Y similar to X is the distance, the coordinate position of the star in Y axis, and dy is similarly the standard deviation or error in the measurement. Okay, so let's take these X and Y values and use these to see what is that thing, how massive is that thing that these stars are orbiting around. So for that we need one more thing. So we have distances, we have time, we also need to know how long. Okay, by the way, this is from one star. This table here shows a position data of one star, and we are only going to use this. So we are going to ask how fast is this star orbiting, and from ESA's data repository, we know that it orbits in 15 years almost. It completes one orbit in 15 years. So now we are going to just use centuries old Kepler's law, and we will now calculate how is what's the mass of the black hole at the center of our galaxy. So just stay tuned. I will switch to Excel now, where I have exported this table. So yeah, so what you see here is time as I was showing in the presentation in the first column, then X position, then Y position. Y position is here, X position is here. Now the data in the table was given in milli-arc second. That's angular distance. We want to convert it into linear distances. So we have the scale bar which they had given. So I have just here multiplied the scale bar and have gotten the X and Y positions of the given star in light days. So now our unit of distance measurement is light days. Okay, so what we are going to do now is just let's just plot it. Let's see how the trajectory is. So I'll just insert a chart here. Okay, yeah, so what I have plotted here is just a scatter plot of X and Y coordinates. They are in light days. The unit of distance in X and Y is light days. Okay, so now this looks a bit pathetic, but we have only this many data points, so it's fine. This looks a bit elliptical, that's for sure. So if you remember Kepler's law, Kepler said that the period of any body that is moving around in orbit around a massive particle object, the square of that would be proportional to the cube of the semi-major axis of the orbit. So assuming all orbits are ellipse, and circle has to be a special case of ellipse. So let's look at so we know the orbital period already, which is 15 years. And we want to know the semi-major axis. So it looks like in this direction we will get our major axis. We should find out what is the half of that. So let's select this point. Can you see my arrow?
Yeah.
Yeah. So let's select this point as our one end of the major axis, and let's select this point as the other end of our major axis. So now we want to find out the distance between these 2 points. And if you just quickly recall how we can do that in a XY Cartesian plane, we just need to take the differences of the X coordinate and difference of the Y coordinate, square them, add them together, and take a square root. So which is what I have done here. So if you look here, x1 is the coordinate. I'll go back here and it will show me the X coordinate. If you can read the flag that has just popped up, minus 0.533 is the X coordinate and 0.123 is the Y coordinate. So that's my x1, y1, which I have put here, x1 and y1. And x2, y2 would be 4.264 and minus 6.806, which I have put here, x2 and y2. So to calculate the distance, that should be our major axis. If you look at the formula bar, it's just that what I explained just now. You take the difference of the x, take the difference of y, square them individually, add them, and then take a square root. So that turns out to be 8.42 something. That's our major axis. And if you want the semi-major axis, then you have to halve it. That comes out to be 4.21373. And the unit is the same, light days, as it is of the x and y. Okay, so the semi-major axis for this star orbit is 4.21. Now I have put some constants here. C is taken to be 3e8, pi the constant, the gravity constant 6.67, orbit period. Orbital period is actually 15 years. So what you do is you take 15 years, multiply it by 365 days, multiply it by 24 hours, multiply it by 3600. So you get in seconds. So everything is SI here. And similarly, semi-major axis, which is our A, will be equal to whatever this is, since it's in light days. Multiply it by the speed of light, which is this one. Multiply it by, since it's day, you multiply, and the C is in per second. So you multiply it by 3600 to get for 1 hour. Multiply it by 24 to get for 1 day. So you get semi-major axis in meters and orbital period in seconds. Rest all are SI already. So now Kepler's law gives an equivalence between the orbital period and the orbital period, square of the orbital period, and the cube of the semi-major axis. And the formula is something that that would be 4 pi square a cube. So that would be, you multiply 4 into pi square, again multiply it by the a cube. So you multiply it the cube and then divide it by the square of the orbital period. So now the square of the orbital period, which is this, multiplied by this again, multiplied by the constant of gravity, so which is this. And there's some mistake here. I forgot a bracket somewhere. So if you take Kepler's law and then input just these values, what you get here is 3.45 into 10 raised to 36th in kilograms. So that is the mass of the combined system here, which is the star of our table, and whatever is in the center, the focus of the elliptical orbit. If we consider the mass of the star to be negligible in comparison to the central mass, then this is basically the mass at the focus, and that is equal to almost a million solar masses. So there you go. So here, what we started with was just the coordinate table. We just knew the position of the star and when the star is at that position. And what we could find out from very basic calculation is what's the mass of the thing that is this star is orbiting around. So that's something that is that's pretty cool, I think. That also is very powerful in the sense that you can. So I was saying that a very simple, it's a simple Excel compatible calculation can allow us so much insight into something that is not easy to measure for amateurs, but the data is still out there, and maybe we can discover something too. And I think that's a note where I would like to end my talk. I would like everyone to be encouraged to try tools, try looking at the data, uh, try like for example, many people process images, and that often brings out some details, some information that the professionals or academics can miss. So the data in current times is open and out there at most places, and you should feel encouraged to try it. There's so much information out there. So yeah, I would like to end here, and I would happily take any questions. Thank you so much for your patience through the talk. It got interrupted many times, and that's not ideal. But yeah, that's about it. Okay, are there questions?
Hey, thanks, Aditya. I think there were a couple of questions in the chat.
Okay.
So one of them was, in the experiment where there was an helical, I mean, there was a gear, and we could measure the speed of light. So how did he make sure that 8 kilometer was the distance, and was it a laser light or something else?
No, 8 kilometer was a ground measurement of the distance, in the sense that he knew, or the team knew, how far they are placing the mirror from the gear system or the light source. So in that sense, the distance was known, and the beam that they created of light had to bounce back from that mirror, and that mirror only, to be able to return back to the gear. So that had to be ensured. But once you ensure that, you know that the beam that you're sending off from this side, from this end into the mirror, is the one that is coming back. And the distance is known because you went and placed the mirror at the other side of the mountain.
Okay. So was it a laser light, or was it something else?
This was done much before lasers could be theorized, or even invented. These were lights that were made into beams to allow linear propagation.
Okay. I guess, Sunil, that should answer his question.
Thanks, Aditya. But still, Aditya, you think that
Yeah, Sunil.
8 kilometers is still far, actually. It's too far. Considering those times, right? Still finding that 8 kilometers is somehow not able to visualize.
It's well, so these were done at the end of 1800, I think, and Michelson, Fizeau, and there was another one who was contemporary of Fizeau, Foucault, Leon Foucault. These guys were doing experiments with testing not just the speed of light, but also if the speed of light is affected by the motion of the medium. So in fact, that's a really good question. I think I'm still going around the question, but what I'm trying to say is that the experiments were surely done at that time. This was done in 1850 something.
One more thing is there were lighthouses by then, right? So lighthouses always used a very concentrated beam of light. They used huge concentrating mirrors, concave mirrors,
Perfect.
to concentrate
Yeah.
light source into a strong beam. So probably those kinds of lights were used.
Yes. Yeah, I think that's very plausible. Yeah, thanks, Chinmay.
Yeah, thanks, Aditya and Chinmay.
Yeah, Sunil. Thank you. Any more?
Yeah, I think there were some questions on how the RPM was adjusted to get the gear and those stuff.
So gear, the number of teeth were kept large so that the resolution of the gear is fine. And if the beam is narrow enough, then you can manage to cut it with the teeth. The teeth are not so small that the beam passes through, but the teeth are not so big that you need to rotate it really fast. So high resolution gear allows you to go at lower speed. So as you saw that the number of teeth was 720, and that allowed the gear to be rotated at manageable RPMs, 12 RPM. That was 12. Sorry, this is 12 per second. I think I made a really big blunder. That was still manageable because there were powered machines by then.
Where would the error come from? Error in measurement of speed of light.
Error would be in the placement of the mirrors, in the, let's say, the distance is not right, or in the placement of gear, or how you're cutting, measurement of the rotational speed of the gear, and so on.
Okay.
And then there are distances. Sorry.
Okay.
And then there are distances that are not taken into account, like the distance from source to the first bouncing mirror, and so on. So these are minor errors. So Senthil has asked, where can I get this data of star movement in center of our galaxy? So this data that I showed is from European Space Agency, and they, I'm sure, also have other data made available. There are papers using this data. I mean, the scientists who did the experiments with these data. You can go to their papers, and then you can find link to their data repository. So Manish is asking, as per Kepler's law, can we take sun at the focus and carry the area swept from both the points? Yeah, absolutely. So you can. That's one of the ways you can calculate the mass, for example, because all orbits can be approximated with ellipse, or all stable orbits can be approximated with ellipse. So Kepler's law would follow. Sure, it was. Except these hiccups, I hope everyone got majority of the content of the talk through. I'm sure the talk will be uploaded on YouTube in time. Over to you, Vishwanath. Thank you so much for giving me this opportunity.
Yeah, thanks, Aditya. I know that we had some connection issues and interrupts. So what we will do is we will trim out those interruptions and then have a clean video and upload it in YouTube for people who have joined this session, and as well as people who couldn't join to view. So that should help a lot. And yeah, once again, thanks a lot for agreeing to this session, and at least giving a fair idea of what these experiments are. A couple of experiments even I didn't know, like especially the torsion pendulum and the mountain and the pendulum to measure the density of Earth. It was very insightful for me, and it actually inspires me to go further and try to find out more knowledge about it. So definitely it is helpful, and we can actually have this additional discussions on around these experiments in Telegram group and as well as WhatsApp group.
Yeah.
Thank you once again, Aditya.
Yeah. Thank you, everyone. Thank you, Vishwanath.
Thanks, everyone. Have a great weekend. We'll connect again in next session in 2 weeks. Thanks, everyone.